All right, let's talk about a revolutionary shift happening in computing right now. It's a change that's inspired by, believe it or not, the most powerful and efficient computer we know of, the human brain. We're going to explore how building computers that actually think a little more like we do could solve one of AI's biggest and kind of hidden problems. I mean, you've seen it. Artificial intelligence, especially these huge language models we're all playing with, has completely upended our world. It's writing code, it's making art. These models are doing things that are genuinely jaw-droppingly impressive. But behind all that incredible power, there's a growing crisis, a hidden cost. The sheer amount of energy and computational power these things demand is becoming, well, unsustainable. We are slamming right up against what some researchers are calling an energy efficiency wall. Now, to really understand why this is happening, we've got to look under the hood. We need to talk about the fundamental design of pretty much every single computer on the planet, a design that's now becoming a major roadblock for the future of AI. You know, for almost 30 years, the AI revolution was basically on hold because we just didn't have enough raw computing power. And yeah, today's hardware is amazing, but now we have a totally different problem, a massive energy gap between what these AI models need and what our current computers can efficiently give them. The problem isn't just the chips anymore, it's the design itself. So this design is called the von Neumann architecture. It has been the gold standard for decades, and it powers everything from your smartphone to the biggest data centers. And in this model, the brain of the computer, the processor, and its memory are two completely separate things. And that separation, that's the root of the entire problem. This really lays it out perfectly, right? The difference between a computer and a brain. In a normal computer, the processor is like this frazzled librarian constantly having to run over to a giant library, that's the memory, to grab a piece of data, run back, process it, and then run it back to the library. This constant shuttling back and forth is slow, and it burns a ridiculous amount of energy. Our brains, though, they are masters of efficiency. They do the computing right where the information is stored. There's no separation, no running back and forth, and no traffic jam. This constant back and forth actually has a name. It's called the von Neumann bottleneck. And as AI models get bigger and bigger, this bottleneck is becoming, as researchers at IBM put it, by far the most severe roadblock for modern computing systems. So, if that old architecture is the problem, what's the solution? Well, this is where it gets really cool. Researchers are turning to a whole new way of thinking, directly inspired by that super efficient computer we all have inside our skulls. And this is the big question that's driving a whole new field of research. What if, instead of just trying to make our old designs faster, we design hardware that fundamentally copies the structure and function of the human brain? And that, right there, is neuromorphic computing. It's an approach that basically throws out that old, separated design and instead builds chips where artificial neurons and synapses compute and store information all in the same place. And the main benefit is so simple, but so powerful. By doing the computation right there in the memory, you completely get rid of that data shuttling bottleneck. You just erase it, and you save an enormous amount of time and energy in the process. This whole approach is built on a few really smart principles. First, you've got that in-memory computing we just talked about. Second, it's event-driven. That just means parts of the chip only power up when new information actually arrives, kind of like how our brain's neurons only fire when they need to. It also uses stateful neurons that can remember past information, which is, absolutely essential for things like language. And finally, it uses low-precision math, which is way more energy efficient for the kinds of jobs that AI is really good at. Okay, so this all sounds great in theory, but does it actually work in the real world? Well, a recent experiment put these ideas to the test. They basically set up a showdown between the old way of doing things and this new brain-inspired way. Researchers wanted to see if a custom-built neuromorphic system could actually beat a top-of-the-line conventional system at a task that is at the heart of modern AI, running a large language model. So let's meet the contenders. In one corner, you've got the brain-inspired system, Intel's Loihi 2 neuromorphic chip. It was running a special 370 million parameter language model designed to be MatMul-free, which is a fancy way of saying it avoids the super energy-hungry math that standard AI relies on. And in the other corner, you have a top-tier GPU, the Nvidia Jetson, running a standard, similarly sized transformer LLM, the kind of AI architecture you see everywhere, The stage was set. Both systems were given the exact same job to do. The question was, which one would be faster, more responsive, and more efficient? The results? Well, they were pretty staggering. The test was something called autoregressive generation, which is the core function of any chatbot. It's about creating text one token or one word at a time. This is what determines how fast and responsive an AI feels when you're talking to it. And right out of the gate, the neuromorphic system just flexed. It had nearly 3 times the throughput. That means it could generate words almost 3 times faster than the conventional GPU. But get this. It achieved that incredible speed while being more efficient. The Loihi 2 system used 2 times less energy for every single word it created. So it wasn't just faster, it was way more efficient. Okay, so speed and energy are huge wins. But for an AI you're actually interacting with, there's another thing that matters just as much: latency. How long do you have to wait for the AI to even start talking back to you? We call this the time to first token. And just look at this difference. The standard GPU took 659 milliseconds to spit out its first word. The Loihi 2 neuromorphic system, a mere 99 milliseconds. That's over 6 times faster. This is the difference between an AI that feels laggy and one that feels instantaneous. So what does this all mean? I mean, these aren't just small improvements. This experiment is pointing to a fundamental shift in how we're going to design and build the hardware that powers the next generation of AI.
And the implications for all of us are huge. First off, it means we could soon have insanely powerful AI running right on our phones and laptops without needing to be connected to some giant power-guzzling data center. That leads to faster, way more responsive chatbots and voice assistants that feel truly real-time. It means the entire AI industry could drastically shrink its energy footprint. And maybe the most exciting part? This kind of efficiency could finally let us build AIs that can do complex, long-term thinking, not just in a server farm, but right here with us. This brings us all the way back to where we started. For decades, we've built computers that are incredibly powerful, but in a very real way, deeply inefficient. And this new research suggests that the blueprint for the next giant leap in computing, well, maybe it wasn't something we needed to invent from scratch, because it's been inside us all along. The future of AI might just be built in the image of the human brain.